All right, welcome back. So I got a review key that I'll post for everybody who turns it in. And so a good idea to watch this before the assessment. But two different parts, free fall and then Newton's law. So in free fall, we want to remember that all objects accelerate equally. Um, so the force of gravity isn't the same on them, but they do accelerate equally. And then when we're doing some of the math with this, so when we got to find the time an object is in free fall, I put the equation in ahead of time, but time is going to be the square root of 2d over a. So you got to make sure to remember that a is going to be 10 meters per second squared in free fall. And remember in free fall, we're neglecting air resistance. So that time equation is very useful when we look at solving things. So here we got Jason bungee jumping. So while in free fall, how quickly will he accelerate? So this is just, the standard value, 10 meters per second squared. So then how long is it going to take him to fall 100 meters? I put that the answer is not 10 seconds in there because that was what some people were making the mistake about. But so here's where I would use this formula from up here. So I'm going to copy and I'm going to paste this. So if you know to use that formula, this becomes pretty straightforward. So now I've got I'm going to just type square root because it's easier. So square root of 2d, so 2 times 100, and that is divided by acceleration of 10. So 2 times 100 divided by 10, the square root of that. So square root of 200 divided by 10 of 20. And the square root of 20, let's see, it's got to be between 4 and 5. Let me plug that into the calculator really quick. So 20 square root 4.47 seconds. And then how fast is he going there? So now we know that he's accelerating 10 meters per second each second. So if he is falling for 4.47 seconds, his velocity is going to equal acceleration times time, which is going to be 10 times 4.47. And so that's going to equal, he's going to be going 47 or 44.7 meters per second. So that's how we do that first one. So now we have the ball toss. So we throw a ball, it's in the air for 3.4 seconds. So the time to go up, is going to be 1/2 of the total time. So this is going to be half of 3.4, which is 1.7 seconds. What was the initial velocity if we threw it up? So remember, if we throw a ball up and it takes 1 second to get to the top, it must have started at 10. If it takes 3 seconds to get to the top, it must have started at 30. So here it took 1.7 seconds to get to the top. So the initial velocity was 17 meters per second. Or if you're thinking math, you're taking the time to go up times 10. And then how fast was it going when you caught it on the way down? So remember, the trip up is the same as the trip down. So if it started at 17, gets to 0 at the top, by the time it comes back down and I catch it, it's now going 17 meters per second again, in the opposite direction. So this is a very conceptual question, one you don't have to do any math for. How high up did the ball go? So now I want to know the distance while something's accelerating. So I use that 1/2 a times time squared. Where's my caret? I actually can't stand the caret, but it's easier to type. So now I'm at half of acceleration of 10 times my time, and I want to use just the time to go up. So that is 1.7 seconds squared. And I'm just going to reformat that. So I get that. And then I just got to plug that into my calculator. So if you know how to do that, then, so now I'm looking at 5 times 1.7 squared, and that gives me 14.45 meters. How much total distance? So now we know that the ball went up and then it came back down. So the total distance equals 2 times the chirp up, the D up, which is 2 times 14.45, which is 28.9 meters. And then the ball's total displacement. So you remember displacement is the vector version of distance, and so that would be a positive 14.45 and a negative 14.45. So total displacement is 0. So that's our free fall stuff, and I'd encourage you to look over your free fall lab and worksheet that we did with that as well. So now moving on here, imagine we repeat the ball toss from above, only you do it while running, no air resistance. Describe or draw the path the ball takes and where it lands. So this is like from our inertia mini labs. So the ball lands in your hands. Remember that video we watched where they threw the ball up from the back of the truck, and it takes a parabolic path, meaning that, and if you put in a shape, it would just be, it takes like the arc right there. So, and that's because it has horizontal velocity that from when you were running with it. So difference between an object's mass and its weight. So weight changes based on location. And a good example of that is if you were to travel to the moon, or if you were to go to the top of a mountain even, versus sea level, your weight is different because the force of gravity on you is different in those situations. So you guys would have typed those answers. I just said them out loud there because I want to save time on this video. Why is it a bad idea to tailgate the car in front of you when you are driving a heavily loaded truck? So you have more inertia and it's more difficult to stop. I learned that when I was in college and I was driving my friend's van through the mountains, and I almost got in an accident because I had to brake way differently than when I was driving my own car. 1 kilogram physics book weighs how much? So if you remember, weight equals mass times gravity. So mass of 1 kilogram times acceleration due to gravity of 10 meters per second squared. So this is 10 newtons. So remember, when you're calculating weight, you just take the mass times 10. This problem, which I really liked, was challenging. It shows the velocity over time here, but it's a great application of Newton's first and second law. So during which time intervals are forces acting on the object balanced? So balanced forces mean no acceleration. So that's any time we're at a constant velocity. So this is B, D, F, and H, because the velocity is constant, it's plateaued. When is there a net force? So we know from Newton's second law that a net force causes acceleration. So that's all the other times, A, C, E, and G. When is the net force directed towards the right? So a positive acceleration, meaning I'm speeding up. So out of these 4 that I answered for 10, I'm speeding up at A and E. And then acting to the left, meaning I'm slowing down. So that is C and G. And then really similarly, now just instead of a graph, we have a dot diagram here. So I have to do the same principle. So forces are balanced when it's a constant velocity, which is A, C, G, and I. And then net force is when it's accelerating. So when is it accelerating? It's accelerating during B and D. Maybe I left out E up here. I apologize because E looks like it's stopped. So this was B and D and F and H. So when is that force acting towards the right? So a positive acceleration, meaning speeding up, which is B and F. So B and F, and then the net force acting on it towards the left, meaning it's slowing down. So that is D, it's slowing down, and H, it's slowing down. So D and H. Cyclist is pedaling, so at a force of 100 newtons pushes her forward, 50 newtons of friction, 50 newtons of air resistance opposing her. So the net force here is, if she's got 100 newtons going forward and then 50 plus 50 going the other way, so the net force is 0. And then if we have a net force of 0, acceleration is also 0. And so some people did some math for 17 and they didn't need to because that's more of a conceptual question. C involves some math because now she's pushing forward with 200 newtons, still has 100 opposing her motion. So now the net force equals 100 newtons, and I'll use Newton's second law to figure out her acceleration is net force divided by mass, which is net force of 100 newtons divided by her mass is 60 kilograms, it says in part B. So 100 divided by 60 is going to be 1 and 40 left over, so 1 and 0.67, oops, 1.67 meters per second squared. How much thrust or force from the engines does a 1,000 kilogram airplane need to accelerate at 500 meters per second against 1 million newtons of friction and air resistance? So big numbers here. I wish I had smaller numbers, but I don't. So I have the acceleration and I have the mass. So I know the net force equals mass times acceleration. So that is 100,000 times 5, so 500,000 newtons. So if the net force on her is 500,000, friction and air resistance are 1 million opposing her motion, then that must mean that the engines exert a force of 1 million plus 500,000. So we got a comma in there. So I just added those together. So that's like the elevator problem we had previously, because if the engines are exerting 1.5 million and there's 1 million opposing that, I'm going to have a net force of 500,000. Unit of force is the Newton. Unit of mass, kilogram. How much force required to give a 2,000 kilogram car an acceleration of 3 meters per second? So this is just Newton's second law. Net force equals mass times acceleration. So 2,000 times 3, 6,000 newtons. Equal force is applied for the same amount of time to a 2,000 kilogram car and a 4,000 kilogram truck initially at rest. Which one will accelerate more? So 2,000 kilogram car will, because it has less mass. Force of gravity acting on an object is called its weight. And then I'm going to make a second video. It's only going to be a couple minutes just so you can get the last part here because this one's going to cut off.